calls within function calls. A bunch of nested calls in a function call. And basically, if you had three in a function call and you had three parameters and all three of them were function calls, it did the rightmost one first, then second, third, fourth. Is that because, so does the compiler or whatever's reading it read from right to left?
No, because it wants to push things on the stack in the right order, but without extra work. So it's basically the compiler being lazy. Okay, so that's a good question to ask related to this class too. So how was debugging B?
I didn't have to do that problem, so it's fine.
Okay. I couldn't stay because I had a union meeting at exactly the same time, and both places have pizza, so I have to choose like Costco pizza. What kind of pizza did you get?
They got Domino's.
Okay.
They got like 6 different pizza types.
Okay. Well, I'm trying to go vegetarian now, so I cannot have
there was
cheese.
a veggie pizza, but I'm sure it wasn't vegetarian. There's cheese on it.
Okay.
Oh wait, no, it's cheese. Cheese allowed vegetarian.
Yes, but not vegan.
Not vegan.
Yep, not vegan.
So vegan pizza must be really sad.
I think there's no such thing as a vegan pizza because you cannot have cheese nor any type of meat.
There's a lot of places with fake cheese.
Huh?
There's a lot of places with fake cheese. My girlfriend's been vegan.
Fake cheese?
Vegan cheese.
Soy.
Vegan cheese? Soy cheese?
Most of it's soy, but there's starting to be some pretty good ones.
Some pretty
Z pizza's pretty
oil.
good. My girlfriend's been vegan for 20 years.
Okay. So this is obviously unrelated to this class. My wife and I were watching one of these movies that talk about the whole food vegetarian diet thing, which at certain places in the movie I thought I was watching a movie about a cult. Okay, some way it resembles that. But the interesting part is it's also somewhat science based, and they talk about how cheese is one of those foods where you get addicted to it. Because the stomach acid, when combined with cheese, would actually give you chemicals that would give you a high. Not quite as much as drugs, but it will still give you a high. So you actually get addicted to cheese because it gives you this sensation, and your brain associates cheese with this really happy feeling. So it's really hard to kind of get out of cheese. Once you get started with cheese, it's hard to get out.
That's a fun phrase. Get out of cheese.
Get out of cheese, yes.
Just say no to cheese.
Just say no because it fries your brain. So the
Cheddar Man.
so the movie that I watched is called What the Health, and the very interesting. I'm not that much into healthy eating and stuff like that. And I go like, I don't need to live long as I die quickly. And painlessly. It's good,
Yeah.
right? So that's my philosophy. But
The only yellow ones.
But you have people to look at.
I have insurance.
Okay.
That's what life insurance is for. But anyway, what about this show that kind of turned me to kind of look into vegetarian diet a little bit more has to do with the relationship between the government, the food industry, and the drug industry. They look at the American Heart Association. They look at the Diabetes Association. They look at all these associations, that are supposed to give people advice, like eat this kind of food, and you will basically not have heart issues and whatnot. And every single one of these associations receive money from the food industry and also from the drugs industry. So when you look at the diet that they do promote, and go like, yep, if you want to prevent diabetes, eat this kind of food. It's actually the kind of food that would actually aggravate diabetes.
Make you buy the drugs from the drug industry.
For life. Okay. So that is the part that really got me. Is like is that part. Okay. Saving the animals. Yeah, I guess if I don't have to make animals suffer unnecessarily. Okay. Saving the planet. Okay, kind of cool. But what really got me, is the collusion between all of these organizations. It's like, okay, up yours, I'm gonna eat plants.
Don't eat your plants. Grow your own.
Well, that's what I've been doing over the weekend. Is my wife and her sister put about 40 tomato plants, and I had to chop those up and basically put those into a big, huge compost pile. I got one of these chippers. You just put stuff in and it will chip everything. And if you put wet tomato plants in it, it will give you tomato plant paste, basically. It's kind of like putting a tomato plant through a blender, which is a little bit too much, So later on, I found a different technique to cut these up with a good old machete. Just put it in the compost pile and go keep doing this. So I'm pretty sure my neighbor were having some issues. Like, what is he doing over there? He's keep doing like
It's a good workout.
like that. So anyway, regarding the homework assignment, are there any questions about the homework assignment? I hope you guys have started on it. Not yet. Okay, you got 1 week to turn it in, so now may be a good time to start working on it because we only got one lecture left. Okay, Wednesday is our last lecture for this class. So we're almost there. Okay. Now I do want to answer the question that Jake asked a little bit earlier, which has to do with the ordering of calling functions when you have nested function calls, not recursive, okay, but nested function calls. So let's go ahead and take a look at this example because it really has something to do with this class as well, because it has to do with how things are ordered on the stack and what is the easiest way to keep that order. So what we'll do is we're going to look at a kind of simple, sample program. So we'll look at this sample program called, I'll just call it nested. Okay. And to make this work, okay, to make it show, what I wanted to show, I'm going to have, standard I/O, basically C in, C out in C++. Okay. And this one I'll have a F1, which doesn't take any parameters. And it does return just 1 as a value, but before it returns that, I'm going to make it print, okay, in F1. Okay, that's all it's going to say is F1 is getting called, and then we'll have a copy of this. Okay, 5, 6, and we'll call it F2. In F2, it returns 2. Okay, and now we have F3. F3 is going to print, okay, I'm going to copy these 2 lines, and we'll say F3, turn 3, there we go. All right, so now we have, sum, and this summation is going to take, 3 components, 3 parameters. Okay, so we'll take N1, N2, and 3, and then we'll do a copy here. And this is just returning N1 plus N2 plus N3, and this is sum. There we go. And then main doesn't do much. All it does is to call sum. Okay, we can have our integer eggs so that we can store the value. So it's sum F1, F2, and F3. So now the question is, what is the call order? Now, obviously, sum has to be called last, okay? Because we have to call the 3 other functions first. So the question is, which one is it going to call first? Now, you have to kind of think about this from the perspective of what we have learned in this class. The last parameter has the highest address, which means it has to push first. The first parameter has the lowest address, which means it has to push last. So that means, unless you want to do a whole bunch of extra work, you want to call F3 first, and then push the return value of F3 on the stack. Then you call F2, push the return value of F2 on the stack, call F1, push the return value of F1 on the stack. Then you just call sum, you're all done. Now on the other hand, if you say, oh, but I read from left to right and I'd like to call F1 first, then you need to find a place to store the value of F1. Then you call F2, find a place to store the value of F2, call F3, and then finally you can now construct your stack. Do you see the problem of doing it from left to right? But if you do it from right to left, it's the right order to begin with. So what we'll do is we'll compile this program and let it run, and then we'll see how the sequence of calling these subroutines and see whether the C compiler is really doing what I said it would, which is basically you doing the least amount of work to get it done. Okay. So gcc-o nested C, and sure enough, it calls F3, then F2, then F1, and then calls sum. Because it's trying to do the least amount of work that it has to. Is that making any sense? So that was a good question because it really helps to illustrate what we have already talked about in this class. But this brings up another question, okay? What if F1, F2, and F3 have side effects? In other words, you're passing some pointers to these particular subroutines, and they modify the same objects pointed to by those pointers. Then the ordering may become important. You may actually want to call F1 first, because the side effect of F1 is what F2 relies on, and then the side effect of F2 is what F3 relies on. So in those cases, you have to be extra careful when all of these functions are called as parameters to another function, because the ordering of the calling is determined by the compiler. It is not from left to right. There's no guarantee that it's done from left to right. If you really need to make sure that F1 is called first, then you probably want to use temporary variables. Store the return value of F1, then you call F2, use another variable to store the value of F2, then you call F3. Now F3 can be in the actual function called to sum because it's the last one. Okay? But you want to use extra means to make sure that subroutines are called in a particular order if ordering is important. Is that okay? Okay. All right. This is also why you don't want to use global variables, because if you use global variables, when you call F1, F2, and F3, there's no visibility that they might actually be related. If you pass pointers, at least you can see, oh, F1 is maybe modifying something that this thing points to. Okay, yep.
Can you go over that point one more time?
Okay. So when you use global variables, just looking at the call itself doesn't tell you what the subroutine is going to modify. When you pass a pointer, even if you pass a pointer, the call to the subroutine itself has the pointer specified, right?
Oh.
Which implicitly says that subroutine really knows where this point is pointing to, and if it's not a const parameter, it can modify it. But at least from the perspective of just looking at the call, you can understand that okay, whatever this thing is pointing to might be modified. But if you're using global variables, you cannot see it at all unless you look at the actual source code of the subroutine being called. You have no idea what it can be modifying.
Okay, that makes sense.
Which makes this problem even worse, because you cannot just say, ooh, okay, they're all using the same pointers. Maybe the ordering of calling is important. When you use global variables, you just don't know. And I can tell you examples of what a massive amount of global variables can do to a project. It makes it basically untrackable, because you have no idea which subroutine is going to implicitly impact which other subroutine, and that's just makes it really, really hard to debug code. And that's why as a general rule, if you don't have to use global variables, don't. The only time I use global variables are the consts. So when you can share constants across all the subroutines by defining those as global variables, because you're not changing those. As long as you're not changing the global variables, it is okay, because you don't have the situations of one subroutine is changing it, the other one is referring to it, and then you have problems.
When do you use defines and when do you use constants? When do you choose to use defines and when do you choose to use constants?
When do I?
Because constants are kind of defines in a way, but when do you choose? I guess if you're using a float, no wait.
It's like, when would you use define over a constant?
Or the other way around.
You mean pound define as a macro?
Yeah.
Aha.
Or the other way around.
Okay, so the idea of pound define. Okay, so you're talking about pound define like this, right?
Yeah.
So the idea is do not use pound define unless you have to.
Could
Go ahead.
I understand define, because define isn't just like a value, right? Like if you put like a equation or like something, it'll like take that and just and then,
Expands it.
Yeah, like paste
Yeah.
it basically.
Yeah, pound define is what we call a macro mechanism, where it is textually expanded. In other words, you can define something that's really wonky. Okay, I can show you something like this. You can define begin, which is a keyword in Pascal, as the open curly brace. It's totally okay. You can now define.
You can make your program.
Yeah. Well, not quite. The
Well,
ordering you
you
cannot
use-
change. So now I can say. Whoops.
Yeah. Mirage showed this. 360.
This will work because this is okay. Macros do not get through a C compiler. It is going through what we call the C preprocessor, or known as CPP. So the CPP, or the C preprocessor, is the ones that will take all the pound stuff and do all the processing. In other words, the preprocessor is responsible to understand that the word begin should be expanded to the open curly brace in this case. The word end should be replaced by a single end curly brace. It will do the pound include, which means it will do whatever is necessary to go find stdio.h, expand the content of that file in place, okay? And and then it will see the word begin, and then it looks up it will look up every single word and see if there's a macro definition. If so, it will change that word to whatever the macro is defining.
It does that before it gets to the compiler.
It does it before the compiler gets control, which also means if you have macros that are wrong or used incorrectly, the compiler message can be very cryptic because the compiler sees the result of the macro expansion, but not necessarily the macro itself. So the error message is only reporting the results after the macro expansion.
Okay.
So it will complain about something that you may not see at all.
Okay.
Yep.
In the IOStream library, true and false are defined, right? As not 0 and 0.
I do not know. I thought true and false are actual keywords in C++.
Other key-
I could be wrong. I don't use C++ that much. GCC has a switch to kind of crank out the actual output after the preprocessor, and I think you can run CPP by itself too. CPP, yep. So there's CPP, which is the preprocessor. So you can put nested.c through it. Okay. So if I scroll back, you can see how. Okay. This is kind of long, so I want to pipe it through less. So there we go. So you can actually see what it's doing. This is the output of CPP. Every line that starts with a pound is automatically ignored by the C compiler. So all this stuff that will start with a pound sign, the C compiler does not see. So you can see that line 216 of this particular file is defining the type def of size t. Okay. You can also see at this point. This will be corresponding to types.h. We have all these type defs, and so on. So this helps the compiler to kind of keep track of which error is coming from which file. Okay. So by the time we get to main, okay, or just a little bit before main, remember we have begin and end with F1. They're now curly braces. This is post-expansion. So the macro is already expanding the word begin to open curly brace and the word end as a closed curly brace. So if I have an error, if the macro expansion itself is wrong, the error message will be about the use of the macro and not about the macro definition itself. And so it can be very confusing to debug those things. Is that making any sense? Okay. There used to be things that you can only do in macro, like in-place expansion of something, but now you have inline functions that can do about the same thing. So the use of macro is usually discouraged. Yep.
I forget the proper term for this, but I know there are competitions for how cryptic you can make your code. Is that how they do it?
You can certainly make things cryptic if you use macro definitions more so than const.
I forget what it's called. I think it's like
Obfuscation.
I think that's it.
Yeah.
Obfuscate your code. Yeah. It's actually very useful.
Well, so that people cannot reverse engineer your code.
Exactly.
But that has to do with the other end of code generation and not so much on specifying the logic. Yeah, so what you're talking about, okay, what you guys are talking about is called obfuscation. Obfuscation.
That's a $10 word.
Yep, I got it. And I got it the first time, which is interesting. Okay,
With the
obfuscation.
Obfuscation.
Obfuscation. Yep. And there are programs to do that. Okay, so when you crank out the actual code from the compiler, it is very difficult to reverse it. Okay, because the ordering of the instructions is not in logical chunks anymore. So that would make it kind of really hard to reverse engineer the code. Given the assembly code, getting back to the C code is going to be very difficult. And there are programs intentionally to do this. You can feed it a well-formed C program, and it will crank out code that is really difficult to reverse engineer. So if you look up obfuscator, and in tools, okay, JavaScript, and here we go. This tool transforms your original JavaScript source code into a new representation that's harder to understand, copy, reuse, and modify without authorization. The obfuscated result will have the exact functionality of the original code. So then, another tool to do this is called Uglify. How does it work? Through a series of transformation, your source code is transformed into something unreadable while working exactly like before. And I think they have.
They typoed exactly.
Yeah, so this is the output of the same code, I guess.
Exactly.
Obfuscate. There you go.
Beautiful.
Now, if someone is to try to reverse this, they can actually look at the generated code, find out what the pattern is, because if the obfuscation process is mechanical, it also means you can find out what that process involves and reverse that too.
So with that output, would that run in a browser?
Assuming that what they claim is true, yes. Because these things are not actual hexadecimal numbers. All they are really is they're just variable names, because they all start with an underscore. So they're really just using a particular variable, in this case, to store an array, and then the function is going to utilize the array indexing and stuff like that to get back to the constants of hello world and log and stuff like that. So it is very mechanical.
That's neat.
Mm-hmm. But it's really mechanical. So I would say that a reverse obfuscator is actually possible. You just need to collect samples of the original code versus the obfuscated code, and if you have enough samples, and the programmer can look through that and find out the logic of how they do it. Once the logic is known, reversing that is not going to be difficult.
So it's like a weird form of encryption.
Yes.
Yeah, but they always say security by obscurity is not a very good way to do it.
No, it's always cracked eventually.
Well, because it relies on the weakest link of that particular way of doing security is really weak. So once they know the method, you're done. As opposed to proper encryption, which means you're using the properties of huge prime numbers to help it to make sure that other people cannot see the content.
Will encrypted code still run?
This will run.
But
Yeah.
with encrypting code, you'd have to what's decrypted.
Yes.
to be able to run.
So if you encrypt your executable,
Yeah.
then you need something to decrypt the executable first, then the decrypted version can run. So that doesn't work well with executables because at some point your executable has to be stored in RAM in order to execute.
Can you encrypt something so that it does something else? Can you encrypt an executable so it does a different program?
The problem is that the CPU can't read encrypted data.
Oh, okay.
It's going to be absolute garbage, and that's the point of encryption, is that without the key, it's always garbage.
Mm-hmm. So people do not really encrypt code. They're not as concerned about encrypting code as to encrypting content, because we are not talking about people who want to copy Microsoft Word or something like that, and that becomes even a lesser of an issue now that most apps are cloud-based. The code is not even running on your PC. Don't bother to reverse engineer. But what you can reverse engineer is how your mobile device or your PC communicates with the cloud application. Because once you reverse that particular process, then the potential return is even more than cracking the application itself, because the potential return is cracking into the whole database so you can see documents of other people. So just imagine if you crack Google Documents and be able to get into the accounts and documents of other people. That is a much bigger potential security risk than, oh, I now cracked Microsoft Word. I can use Microsoft Word for free. Oh, okay.
There was that iCloud.
Why would I want to use Microsoft Word?
Like last year or the year before that, there was the iCloud hack or whatever.
A lot of that I thought was just people not keeping their passwords secure.
That was it.
Now,
They got a hold of a bunch of people's passwords though, manually or via hacking.
is that done by dictionary attack?
I don't know how they did it. Apparently Apple and Sony together have really terrible password protection. Because neither of them seem to be able to keep their accounts fairly strong.
Okay. But are there any questions related to this class? About the homework? Yep.
It's not about the homework, but it's related to the compiler, not the compiler, the processor. On the toy processor, we use 0 to model null.
We use 0 to...
Like on the homework assignments, for when a pointer is null, we just say that's 0. How does a real processor store null?
0.
Just a 0?
Yep.
So how does it know the difference between the value 0 and null?
No, the type is different.
Okay.
Yep. the only difference is the type. So a null is a void pointer is 0 void casted to become a void pointer, and a usual 0 is just the integer 0. So it's only the type that is different, and that's why it makes no difference in assembly language programming, because there's no such thing as type in assembly language programming. 0 is just 0. It is really just literally in an 8-bit processor. It's 8 bits of zeros. That's a 0. It's also known as the null pointer. It's also known as the null character. So it depends on how you use it. When you are about to dereference it and you're just checking whether it is okay to dereference, yes, it is now a pointer. When you send it to something that can print, then it's a null pointer. When you are using add or subtract, it is now an integer. So in assembly language programming, there's no such thing as type. It is all the instructions that determines what you're doing with the values. So that's a good question. Anything else? Now, we don't have enough time, nor the space in the processor to deal with structures. So how do you think your structures, come in play? How do you deal with structures in assembly language programming?
When you have enough RAM for it.
Well, we can do simple stuff, okay? But the question is, how do you represent the structure? What do you think?
Subroutine?
No. It has nothing to do with subroutine. Structures are class, okay? Pick one, because they are really the same thing from the perspective of assembly language programming.
A variable of a struct has its own address, and then it has two other, at least one
It has
other
parts, right?
It has parts inside.
Yep. So the key here is it has parts. Okay. So I'm just going to talk about this. Obviously it won't be in the test because this is too close to the end of the semester. Topics that we talk about today will not be in the test. Will not be in the final exam. And this is 440. Okay. Let me go back and use the proper one. Oh, Java?
Yeah.
I just read it. I went to take
Yeah, Java is interesting, from the perspective of articulation, like which school you transfer to. Sac State is the only school that uses Java.
Yeah.
And I think all the UCs require C++, which creates certain problems at Sac State because they use Java for just about everything except for their systems programming class. So there's a systems programming class where they teach people how to use the file system, use sockets and stuff like that, from the operating system perspective. And that class is split into two halves. The first half is basically teaching people how to use C. And then the second half is the actual topics that they have to talk about. So that's
So I should
yeah.
refresh on Java. I'm going there. I'm going there in the fall. So I
You
guess
go Sac State?
Yeah, so I guess I should refresh on Java.
Yeah, you should, because all of their classes except for systems programming, make use of Java instead of C++.
So if we're transferring there as an upperclassman, they assume we are fluent in Java, or at least know it.
Yeah, they would not. They would assume that you know Java already,
Okay.
because Java is their C++.
Word.
Isn't Google trying to get rid of Java for their Android?
Sure.
I feel like I've tried to do that for a while.
I keep hearing everybody's trying to get rid of Java, but it's still wanted.
At some point, Google's going to replace everything with their own version of it, and then it'll be dependent on Google, and they'll start charging money for it.
Like they tried to make a Windows Java. Talked
It'll
about that.
become self-aware.
Microsoft tried to make their own Java.
Okay. Okay, so let's look at this structure here. Okay, I'm defining this in, let's say, a regular C program. Okay, so this is not related to the toy processor, because we don't really have the efficient way to deal with this, in a toy processor. But yet it is still useful. It's an important discussion. So this is the structure definition itself. So in C and C, you need a semicolon after a struct definition. In C++, you do not need a semicolon after a class definition. So there are slight differences between the syntax between C and C++. So this is how we define the structure. So now the question is, when you actually use a struct like this, okay, so let's say you're in the program in one of the subroutines. This is struct X, and we call this, var1. Okay. So var1 now has these members, right? So var1 has a member X, has a member CH, and has a member Y. Okay? So the question is, how is var1 organized in memory? Which part is where, how do we access these individual parts? So the first thing we can do is to actually write a program to illustrate this. So we'll go ahead and write a program called struct, okay, just to do exactly that. So we define a struct called X. X is the name of the struct, which is kind of equivalent to a class name, except a struct is like a class where everything is public. Okay? And also in C, instead of C++, you cannot have methods inside the struct definition, so you can only have members. Okay? That's kind of like, it's kind of like a downsized class type construct. Okay, so int x ch30. I'm just copying exactly the same stuff from before. Okay, so now we go to main, and then we can do some printf here. So we'll go to, well, I don't really need printf. Okay, so I can just define the struct x. We call it var1. Okay, same as the code in the tablet, on the tablet. We'll do some initialization so that the compiler does not optimize var1 out of existence. Okay, so at the moment we touch it, it has to exist, even though it might complain and say that, oh, you put something into it but you never refer to it. But that's okay, it's just a warning. Okay, so this is my entire program. Are there any questions about this program? It's an entirely useless program, right? But the point is to illustrate what is in a struct, what can we know about a struct, and how do we access members of a struct. That is the whole point of this particular exercise. Okay, So then we can now say gcc-g, because we need to run a debugger to actually make use of this program. Struct.c, gdb struct, and then we look at the program, put a breakpoint on line 14, which is right before the return, run it. Okay. So when you say print var1, GDB is pretty smart. Okay. In other words, GDB says, oh, let me show you all the members of this particular structure. Member X has a value of 0, that's the integer. Member CH is the null character repeated 12 times, and then we have a whole bunch of gibberish after that because it's not initialized. Okay.
Initialize the first 12?
No, it just so happens that we have it. The entire structure is not initialized.
Yeah.
So whatever we see here is just whatever is quote unquote on the stack at the time. Because guess what? Your structures, when you define this structure as a local variable, it also lives on the stack, which is a big deviation from Java. Since we were talking about Java, okay. So if you're transferring to stack state, and this is the way they deal with objects is entirely different. In Java, when you define something as a particular class, it is only a reference. The object does not exist until you create it, or until you use assignment and say that, okay, that reference to that object is now the reference to the same. This reference is referring to the same object. Okay. But we're dealing with C++ here, or regular C, so this is what happens. So now the question is, where are these members? In other words, I can now say, okay, where's var1? Okay, this is the location of var1. All we need to do is to keep track of the least significant 3 digits, because I cannot imagine the other digits getting changed at all. Okay. So without a whole lot of questioning, the first member probably has the same address, right? Because this address, E180, refers to the beginning of the entire structure. But the first member, which is X, probably also has the same address, just a different type. So when I press the Enter key, sure enough, we are looking at the same address, but the types are different. The address of var1 has a type of a pointer to a struct X, but the address of var1.x is a pointer to an integer. But that makes sense because the member has a type of an integer.
How can they have the same address?
It's like an array.
It's a composite.
Well, an array.
That's why you can use pointer syntax when you're calling structures.
Yep.
That's all it is.
Yep. Okay, but I can illustrate it using the other thing just a little bit later. This one is 4 bytes off. Why do you think it's exactly 4 bytes off? Because the integer has 4 bytes. Yeah. Very good. Okay, very good.
Made in sequence.
Mm-hmm. So what do you think? Where do you think is y?
Whatever 30 charges there is.
30 bytes.
It's 30 bytes after 8-4. So that would be 16. So it would be 9, right? And then plus 12. 16 plus 14. So that would round up one more time. So it's going to be A2. It's going to be A2.
But just add 3 to
A4. Okay, so why is it not A2?
Just add
My
3 to
math
8.
was not wrong, okay? It really should be A2 if it were to compact everything, to use the least number of bytes. But this is not using the least number of bytes, okay? The quick way to do this calculation is A minus 8 is 2, okay? And that's 2 times 16, which means there are 32 bytes between the beginning of CH, which is only an array of 30 characters, and the last member of var1. So 2 bytes are actually not used at all. Why are we wasting 2 bytes?
I want to know.
We want to keep everything aligned. That is the reason. Aligned by what? Aligned by 32-bit boundaries or 64-bit boundaries. Depending on the processor, we want it to be aligned, but in this case, it's definitely aligned by 4-byte boundaries. Why do we want to keep things aligned?
That's a char array, and everything in the char array is sequential, right? So if you mess with one of the array addresses, Doesn't that like screw everything up?
That's not the reason.
Yeah.
Okay. All right. So.
If you assign somebody the char array now, I figured it would.
And what do you think this is going to be? If I want to look at the size of var1, what do you think is the size of it?
What was the size of char?
It should be 40.
A char is 4 bytes.
No, the ch.
Would it be 40?
ch is supposed to be 30 bytes.
30 plus 4 plus 4. But
another
it's not.
curveball.
So we got two possible answers, right? We got 38, which is the minimum number of bytes, and then we got 40 based on those 2 bytes being wasted.
Yeah.
So the correct answer is 40. Okay, so let's check. Okay.
Are those two extra bytes part of optimization, or what is that?
It's optimizing for speed. It is part of optimization, but it's optimizing for speed. So let me explain why that is the case. Go ahead.
If that char array happened to be 33 characters long, would we then waste
3
30
bytes.
characters?
We'll waste 3 bytes
3 bytes.
because it will make it consume 36 bytes, and therefore 3 bytes will be unused.
Why 36?
Because 36 is the next multiple of 4 that is greater than or equal to the number of bytes that you want to allocate. In other words, it's always try to allocate so that the members, the beginning of each member, is landing on the boundary of a multiple of 4 in terms of the address. So the question now is, why?
What if you,
So,
so if you make like a array of 1 character,
It will take up 4 bytes.
that's so.
It'll take up 4 bytes. Why?
I'm just wondering why I've never run into. I guess you don't really use pointer division or pointer addition when you're using structures. So I guess I would never have
You could.
come across. I never have them. So I'm just like.
Because when you do pointer arithmetics, it is automatically done for you.
Jumps to the
Oh,
next
that's
one.
right.
Yeah.
But also like, I never with structures. You don't really do like this member plus this member, this member. You always just call each member as you.
Exactly.
Yeah,
you
so
use
never really do
you
it.
access the members by their name and not by the number of bytes they're off from the beginning of a structure. So that's your compiler doing a lot of work for you, because now you don't have to keep track of all those displacements. You don't have to look at these numbers. And in fact, that's also why you do not even know that it will pad each particular member until it consumes a multiple of 4 bytes. So the question now is, why? Why?
Tell us.
Okay. Why do you think a 32-bit architecture is called a 32-bit architecture?
Because it can address addresses up to 32 bits.
Sorry, say that one more time.
Its address, or the number of addresses that it can address, I guess, can be defined by 32 bits.
Okay, so you're correct, but that's not the only reason. Okay, so a 32-bit architecture is called a 32-bit architecture for several reasons. The first reason has to do with the ALU, the arithmetic and logic unit. When you add, you can add up to 32-bit at a time. Okay, so the 2 operands that you use in an add instruction, each one is 32-bit byte, and that is the main reason why we call an architecture 32-bit architecture. Okay. The second reason is usually the address bus is theoretically 32-bit byte. Now I said 32-bit byte theoretically because that would mean the 64-bit architecture has a 64-bit address bus. Theoretically, yes, but in practice, no. Because 2 to the power of 64 is what? A gigantic number, right? It's a huge number. Do you have that much RAM on your PC?
No.
No, not even close, right?
But just because you don't have it doesn't mean it can't be,
But when you store an address, it is 64-bit byte, but when you're looking at the actual address bus on the motherboard, it is not even close to 64-bit byte. It might be 48-bit byte.
Is it because the manufacturers say that you're never gonna try and implement that much, so why even
exactly.
bother?
Why waste copper traces and do all the routing when those copper traces will not be used?
Oh, so are they more like 33 or 36-bit? Because they're definitely not 32 anymore. Otherwise, we'd never be able to address the amount of
Okay,
RAM
so
that we
you
need.
guys are more in touch with this. If you were to buy the super duper gamer, motherboard, how much RAM can it address?
Someone pushed it to 128. I've seen.
Gigs?
Yeah, gigs.
Okay, so 128 gigs. So now the question is, how do you represent 128 gigs? How many bits do you need to address 1 byte out of 128 gigabytes? Okay, so we are looking at 128 giga. Okay, a giga is not really all that much. It really is just 9 zeros. Okay, well, we are looking at the decimal version of this. This is approximately 2 to the power of 10, 2 to the power of 10, 2 to the power of 10, and this we know as 2 to the power of 7, right? So the entire thing is 2 to the power of 37, which also means the actual physical address bus only needs to be 37-bit wide. Not quite 64, right? I mean, this is only 5 bits more than a 32-bit bus, address bus. Okay.
And yet it far outstrips the 32-bit space.
Hmm?
You can, 32-bit processors were like 4 gigs, wow, and now it's.
Well, we used to, think, 4 gigs, why would we even need more than 2 gigs or 1 gig of RAM? And now we are saying, yep, 16 gig is the minimum to run Windows 10 if you want to get anything done. Okay, so that's another reason why a 64-bit architecture is called a 64-bit architecture, is internally when you store an address, it's 64-bit wide. Okay?
Is that limited, again, at the motherboard level, or are the CPUs that Intel and AMD are putting out
Both.
also limited?
It is both.
Okay.
So because the address bus, it comes out of the processor. So if the processor does not have 64 address bits coming out of it, then that is your first level of limitation, because hey, you just do not have that many address bits that you can specify. Yep.
Is that something we'd be able to, for a random processor, we'd be able to look up?
Yeah, absolutely.
Okay.
Yeah, you basically what you do is you look up the pin out of a processor, and you count, the A lines. Okay, so I'm not sure whether we can find it easily here or not. Okay, there's a.
Probably an old one. We'll probably find old processors pin out.
I'm pretty sure the new ones, we can find it too. So i7 pin out. Okay, there will be a lot of pins. Okay, because these new processors have more than 1,000 pins.
1,150.
Okay. But the idea is. Okay, just looking at a quick pin out. That may be a little difficult to find. Oh, I know what. Images. There we go. There. Oh. How come Google has access to it, but I don't?
Those funny images that are like, we have this thumbnail stored in our database, but it no longer exists.
Okay. But anyway, if you look at the pin outs, you will find the address pins, and whatever number of address pins it has, is the limit. So if the processor only has, let's say, 40 address pins coming out, that means 256. No, it's more than that. But that limits how much RAM you can physically add to the system. But what about the data bus? A 64-bit processor implies that it has a 64-bit data bus. Okay, so what does that mean? We have a processor. The i7 processor is still byte addressable, which means when you specify an address, it is corresponding to the address of a single byte. Okay? But the data bus itself is 64-bit wide. What is the implication of that? Every single time you read from RAM, you're reading in 64 bits or 8 bytes at a time. But I only need one. I just need a character. No, you're reading all 64 bits at the same time. You're reading 8 bytes at a time, even if you only need one of those 8 bytes. Is that okay?
So is it actually taking in, even though your program is only taking in, or supposedly only taking in 1 byte, it's not going to just say, okay, here's 8 to 7 sections of garbage or zeros, and then here's your byte that you need.
Well, in terms of the interaction, the processor from your code perspective will only be getting the content of the byte that you need to access.
Okay.
But in terms of bus operation, it is reading in the entire 8 bytes surrounding the byte that you want to access.
It sounds really,
Inefficient?
yeah.
Well, that's not bad. It is
No,
even
that-
worse when you have a multi-byte integer that is sitting across the boundary of these 8-byte boundaries.
So you can't take it in one go.
Exactly. So the issue is
Does RAM defrag itself?
a defrag is not going to help, unfortunately. Okay, so let's say you have 32-bit architecture, so 64-bit is really about the same, and these marks are only here to separate byte boundaries. Okay, so let's say you're trying to pack everything as tightly as possible. You're ignoring the natural multiple of 4 boundaries. So now you have a variable that will span across 2 of these constructs. You have the least significant byte of x being here, the second least significant byte of x being here, the second most significant byte being here, oops, this is a 2, and the most significant byte of x being here. So now your variable x is spanning across 2 32-bit chunks. Okay, so when you need to read variable x, you need 2 memory accesses, not just 1. Is that making any sense? So this is why the compiler is padding the members of a structure so that everything starts with a 32-bit boundary or multiple of 4.
Would, if your char, I'm not thinking of the word for it, array, if that covers multiple areas, would that be a problem, or the fact that it's just
That would not.
increments each time is you're only getting 1 char at a time?
That is not a problem because there's no way around it.
Okay, and you're only getting 1 char at a time,
Right.
so it's like just
Yeah, exactly. So there's no way around it. In fact, what happens is most processors these days do not really access one 8-byte wide thing at a time. It would do it in burst mode. Okay, when was the last time you buy memory for your PCs?
A year ago?
Year ago? Okay, fine. What is the standard at the time? DDR?
Oh, I think DDR4 was out, but it was still kind of pretty
Okay.
expensive and new, so I got DDR3
Okay.
because that was.
So what is DDR?
It's the standard.
Dance Dance Revolution.
Yeah, it is dangerous. You're correct.
It's double data rate, right? It's called double data rate.
So
And how does it work?
Magic.
Put your foot on the little pad when it lights up.
Pixies.
Okay, so the way it works, or the reason why we have DDR, is because individual byte, individual location access is very inefficient. Okay. Every time you want to access a memory location, what do you have to do? You have to specify the address bus. This is where we want to access. You have to specify this is a read or the write operation, right? You have to enable the RAM and go like, yes, I'm talking to you. I want you to figure out, to give me the content at that location. And then you have to wait a little bit because it takes time for the RAM chip to decode the address bus to figure out which location do you want to access. Okay? Once it figures out which location you want to access, it will go to the location, and there's another lag, another latency before the actual content of that location of RAM is presented on the database. Then your processor can sample the database and go like, okay, we got it. And then what do you need to do? If you need to access the next location, what do you need to do? Do the whole thing again, except the address is now 8 or 4 more than before. Is that okay? But you have to go through the whole exercise. You have all the same latency again. You put the address on the address bus. There's a latency before the RAM takes that address into consideration. There's another latency for the RAM to go to that next location, put it onto the databus, and then there's another latency for your processor to read from databus. So it is very inefficient. Double data rate is a cooperation, is an understanding between the processor and the RAM. Okay, and it starts with this. It's like, okay, Jake, let's start with location 478. Okay, and then you will present, location 478 to me, and then without me asking, within a certain amount of clock time, you'll present 47C, which is the next 4 bytes, and then within a certain amount of time, you'll present location 480, which is the next 4 bytes, and so on. And there's no actual interchange of signal, in between. It is just what we call burst mode, because the RAM itself understands that it's in burst mode, and then we do the clocking. It's like, okay, there's the system clock or the RAM bus clock, not RAM bus, but the RAM clock, it will go like, okay, every half clock or every clock, every edge, up, rising or falling edge, I'm gonna go to the next location and present the data of that location. So the RAM itself is actually keeping its own counter and go like, okay, I'm starting at this location, but then for every single clock, I'm gonna increment to the next 4 or next 5, next 8 or next 16 locations.
Do modern programs or operating systems assign memory so that that's the most efficient way? Because I would feel like you could really start just, again, having the RAM tossing unused data towards the CPU, unused locations.
Okay. So when you do burst mode access, like what I just described, you're usually reading in a pretty good chunk of data, like 128 bytes, at least 64 bytes or something like that. So you're basically reading we're reading in 64 bytes, but really, really fast. Okay, much faster than individually reading 8 chunks of 8 bytes. What do you do with these 64 bytes? You just need the next 1 byte. So now you have 63 bytes in addition to the 1 byte that you need. What do you do with the other 63 bytes? You put it into cache. Okay? Have you guys heard of cache?
CAG.
Yeah. There are level 0 cache, level 1, and level 2 caches. Okay, but we are not even considering the levels here. So all the extra bytes are now stored in cache. At some point, the processor goes like, okay, we're ready to move on to the next instruction or the next byte. It doesn't have to go out to RAM anymore because now it is cached.
So is that why cache is so important with modern processors? Is that they're actually, the burst mode loading is that you're filling up the cache as much as you can.
Really fast.
And then the CPU works through it, and then just load the cache again, work through it.
Yep.
Rather than always going out to the RAM.
Exactly. So, but now it also depends on what is the pattern of your instruction, how it is going to access different locations in RAM. Because if you're completely scattered, okay, I'm going to take a few bytes here, a few bytes over here, a few bytes over here, then your caching mechanism is not going to help you. Because of the 64 bytes that you're reading in, you're only using, say, 10 of those, and then that entire chunk is useless. And then you want to read another 64 bytes in, and then use like 10 bytes of those things, and then you toss away the entire thing. Is that making any sense? On the other hand, if your program is completely sequential and is stuck in a loop, hey, caching can be really helpful because everything is being sequential, which means of the bytes that you read in, all of them are going to get used. But caching also means that you can cache multiple pages. Each one has 64 bytes. So as long as those pages are getting used frequently, they will stay in cache. Which also means as long as these things are cached, your processor doesn't have to go out to RAM, which also means the execution speed can keep up as long as the program is kind of stuck in that loop.
So a lot of sections of the operating system remain in cache and are never really referenced from memory.
It's not just the operating system, but also your application,
Sure,
everything, all the code that you run, as long as they have good, what we call locality, then you can make use of the caching ability as much as possible. Yep.
What makes caching so much faster than RAM though? Because you still have to access
because
information.
there are
right?
two, well, okay, the number one reason is cache is on chip and RAM is not.
Okay.
So when you look at a picture of a motherboard, looking for my pencil here. Okay, so when you look at a motherboard, so here's the processor chip, and so let's say this is your motherboard. The processor chip is actually pretty small. Okay, when you look at the actual die, the silicon die of a processor, it's not that big. It's really kind of tiny. And then you have RAM here, okay? You have rows of RAM, what we call DIMMs, dual inline memory modules over here. So when you blow up this portion, when you blow up this die here, a portion of this is cache, but that is that's on the same die. So when you look at the physical distance from here to here versus from here to whatever your actual processor core is, the distance is very different. So that's the first difference between accessing cache as opposed to accessing memory. It's physics. Okay. How many people have taken physics? The electricity type of physics. Do they talk about inductance?
Mm-hmm.
Okay. What is inductance?
Resistance to flow.
Yeah.
Resistant. Okay, that's a good way to put it. resistant to flow, which means
Resistance to change in flow more.
Exactly. So in order to get things going, you have to ramp it up. It's kind of like a flywheel. You cannot just get a flywheel to turn at a certain speed like instantaneously. You have to ramp it up. If you want to stop it, you have to ramp it down. There's no way to stop it like instantly, right? So electricity is the same way. Okay, if you want electricity to flow, you need to ramp it up because of the inductance. If you want it to stop, you also need to ramp it down because it cannot go instantaneously. And guess what? The longer the wire, the more inductance you're dealing with. So that means this wire going from your DIMM to the processor has a lot more inductance compared to this internal trace on the die going from cache to your processor core. Yep.
Do the RISC SoCs that we have on our phones and stuff suffer this same issue now that the DIMMs are no longer
it does
DIMMs?
not, because your phone actually has RAM on chip.
But is it basically this? Is it just massive cache? We just don't call it cache, or
No, because the nature is different.
Okay.
So it's two different things. But your phone doesn't have memory modules being physically that much distance away from the processor core, because your RAM is actually on the same die.
Mm-hmm.
And that's why when you buy a phone, you cannot extend how much RAM your phone has, because it is not a separate chip. You cannot just say, okay, I'm going to replace this chip to make my phone have more memory. It is on die. It's whatever comes with the processor is your limitation. Okay, so this is the main difference. Okay, the distance from memory module to the processor, as opposed to the trace that goes from on the same die from the cache portion to the processor core, is vastly different. So that limits how fast you can change the signal, because if you cannot start the flow of the electrons and stop the flow of the electron very quickly, that limits how fast you can change the signal, and that's your limitation of how fast you can transmit data into cache from memory. But from cache, feeding the core is pretty fast, and there are different levels of cache too. So the second question, which relates to what you just mentioned, is so what is the difference between RAM and cache? RAM is explicitly addressed and cache is associative. Okay, so what is the difference? RAM itself says, okay, if you want to access a particular byte in RAM, the processor has to say, I need RAM at this location. Give me RAM, the content at this location. So RAM itself contains everything, right? It contains, if you have 8 gigs of RAM, you actually have 8 gigs of RAM. So it would look up, okay, which memory module, which chip contains that content, and then which location on that chip has that content, and then it will disclose the answer. Cache, on the other side, stores both the address that is caching and the content at the same time. It's associative. So when the processor core says, hey, do we have the content at this location already cached? It is asking the cache controller and saying, okay, this is the location I want to access. Do we have to go out to memory to get it, or do you have it cached already? So the cache mechanism is an index lookup thing. Okay, it will say, do we have that page already cached? Yes. Okay, so it doesn't have to go all the way out to memory to get it. So that's why cache is called associative, because it not only does it contain the content that it's caching, but it also knows which address is corresponding to that content.
So the cache doesn't have its own address in the same way.
That is correct. It does not have address on its own. So from the code perspective, from the opcode perspective, cache is transparent. You cannot say cache lookup, okay? It's automatic. Your memory controller or the memory management unit, MMU, is responsible to deal with all of this backend stuff. If cache doesn't have it, it will go to memory, then it will cache it locally, and then, but since you only have so much cache, how much cache do you have on the i7 processor, the latest and greatest? We are still talking about, we're measuring in megabytes, right?
If that.
Well, we're definitely megabytes, right?
It's
256
I
megabytes?
think that just
I don't know, every chip that I've seen has been measured in kilobytes and just multiple levels.
There are different levels, but the lowest level, which means the furthest away, usually are in, I think they're in megabytes. So if you look up i7 cache, okay, right here, 8 megabytes of smart cache. Yep, okay, but how much is 8 megabytes compared to how much RAM you have installed on the system that would make use of such a high-end processor? Not a whole lot, right? Such a system probably has 32 gigs of RAM, or at least 32 gigs of RAM. So that means what you can cache is a very small portion of what you can actually store in RAM. Which also means, hey, somebody has to be in charge now and say that you have not been using that page of the cache for a while, and I need to store something new. That has to go now. So the MMU, or the memory management unit of your processor, would also do that transparently. So your code doesn't know about all of this stuff that is happening, but the MMU is very busy keeping track of this stuff. It's like, okay, so let's see which cache entry is recently loaded. We better not kick that out, okay? That one, on the other hand, has been sitting around for a long time. We have not been reading from it or writing to it for a while, and we are reading something new in. Let's kick that out.
So it's got a little timer on each memory space, sort of.
Yeah, it's called MRU, most recently used. So that would be the most common technique or strategy
So
to determine what to keep.
A second table of addresses referred to? Or
It's
loaded from?
in the same mechanism. So when you look up, it will also have that information. But this is all maintained in hardware, so your software doesn't have to do anything like that.
Right. I'm just wondering if this is there actually more memory on cache than what's accessible, and all that extra memory is just used
That
to...
I do not know. I do not know whether the 8 megabytes of smart cache is including the accessory, the attributes or not, or really just the content that you can cache. I would assume the 8 megabytes refer to how much content you can actually cache without the overhead. But that would be my assumption. Is that okay? So this also illustrates why different algorithms can run differently, depending on how we can make use of cache. Okay, this class only has 360 as a prerequisite. How many people have taken a class where they talk about sorting algorithm? I think 360 or 300 talks about sorting algorithms, right? Okay. So when you think about sorting algorithms, quicksort, okay, which is one of the things that most people talk about. It's I think Professor Fox's favorite sorting algorithm. So do you think quicksort is cache friendly or not so cache friendly? In other words, does it have locality? Does it work with things that are really close next to each other or not? Quicksort. Quicksort can be recursive, right? And what does it do? It has a construct called a pivot. Okay, and what does it do with a pivot?
It checks it against the upper and lower bounds.
like finds the highest value on one side, the lowest on the other, and swaps it.
Yep. But the distance between the elements that you're swapping, are they close to each other? Are they always kind of like, oh, it's always next to it? It can be really far away, right? So that means the access pattern of quicksort is kind of all over the place. It's not very, it has no locality. Yep.
Would bubble sort be really cache friendly then?
Yes, but okay, but
Selections
related to
reflect
the big O notation thing, bubble sort natively is much slower compared to quick sort. So bubble sort has a big O of n squared, n being the size of the array, which means every time you double the size of the array, you'll be quadrupling the amount of time it takes to sort it. So even though it has locality, it does not help with how much time it's going to take. It's still very inefficient. But you can compare two algorithms, both having the same what we call the time complexity. One is quicksort, one is called merge sort. Okay, they both have a time complexity of n log n, which means they are the most efficient sorting algorithm they can ever find. But one has locality and the other one does not. Merge sort has locality because when you do merge sort, you are
Splitting.
You're splitting. So basically, you're going through an array in a very sequential way, and you split it into two different arrays. But when you split, you're also filling in the other two arrays sequentially. So it has locality. There's one locality going in this direction, and then two localities going in these two directions. But nonetheless, there's locality. When you do the merge, it is the opposite. So you have the two arrays turning into feeders, and then you have the one single array being the sink of the two. So you have this thing going to here, this thing going to here, this thing going to here, and so on and so forth. But there's locality again. Okay, you're reading sequentially from the two arrays that are serving as the feeders, and you're filling in the destination, also sequentially. So there's locality. So when two algorithms both have the same what we call time complexity, but one has locality and the other one does not have locality, the one that has locality would make better use of the caching mechanism of a processor, and theoretically, it should run faster. So quicksort, as cool as it is, okay, in many ways, may actually be slower compared to merge sort because of the lack of locality once you take caching into consideration. Yep.
How big of an effect does caching have on performance? Because
big time.
well, again, because of locality and stuff, when my computer's running on idle or I'm running, web browser or something, I don't feel like there's enough memory being used to really take advantage of the caching, as opposed to when I open up Adobe or Maya or something, where I'm starting to use, 8, 10, 12 gigabytes of RAM, in which case I've got all that blocked for that burst mode and that caching to really start working.
Well, okay, if you look at Maya, or if you look at Photoshop, it easily deals with gigabytes of data. So your cache is only 8 megabytes, right?
Right.
So unless what you're processing has strong locality, or the code itself has really strong locality, it's not going to help out that much. It also depends on how the program is compiled. Okay, now we are all in this class, right? We understand how C programs boil down to assembly code, right? So if you use the good old top-down design approach, where you have each subroutine only having like 20 lines of code, but you have more levels of subroutines, that actually defeats the whole purpose of locality too. Because now you have to call. What is a call going to do? Tell me what the call has. You guys know the yeah.
Parameters of address.
Well, okay, it has access to a lot of different locations because you have to deal with the stack too, right? You have to push the return address, then you go from the caller to the callee. The distance between the caller and the callee is most likely beyond a page of a cache. Okay, so they're not going to be on the same page. So now you have all these calls and returns and whatnot, and every time you call, you need to access the stack because you're pushing the return address. Every time you return it, you access the stack again because you're popping the return address. So if you look at the access to memory and locality, this is not going to be, there's not a whole lot of locality. As opposed to what we call monolithic programs. A monolithic program will be a subroutine that is about 500-600 lines long because whoever wrote it decides not to use subroutines to do abstraction. So it is horrendous when it comes to maintenance, but when it comes to runtime, maybe it has more locality because now all your loops, all your variables and whatnot, they are really close by, and there are no calls in between. Yep.
Wouldn't your assembly compiler simply use your subroutines as a form of abstraction, and when it actually compiles, it'll just insert?
Not, okay, it will try to do that when you use the word inline, when you define the subroutine.
Okay.
Okay, so there's the keyword called inline in all compilers because it is a part of the NCC standard. So when you use the word inline, it basically tells the compiler and go like, if it is possible, expand this code inline so it is not actually a caller calling a subroutine. But there are certain cases, so it's up to the compiler now to decide, okay, is it viable to do it? If not, then the compiler would just say, okay, we're keeping this as a real subroutine and we're just going to do the call.
So is that how they get around the whole dilemma of monolithic versus subroutine based
No.
coding? No? It's just whatever the coder feels like?
It's whatever the compiler feels like it. Most of the time, if your inline subroutine consists of a single return, it will actually be inlined. On the other hand, if it contains a loop of some kind, it's usually not inlined. Now, in terms of loops, okay, there are also other things to consider. I know we are running out of time. There's a concept called pipelining in processors. Okay, no, the toy processor obviously has no pipelining either. But the thing about pipelining is you're executing instructions in sequence. Do you guys know how pipelining works in an assembly line? Okay, so let's say you have 4 people in the assembly line and you're assembling Furbies. Okay? And there are several ways to make use of 4 people. You can say, okay, each person is going to assemble the Furby from start to finish. Okay, that's one way to do it. But you can also do it, we can also do pipelining, which means the first person is going to do the first part of the assembling, the second person will do the second part of the assembling, and so on. That's pipelining. But pipelining is doesn't like branches. Because whenever you have branches, especially conditional branches, it breaks the pipe. Because the next instruction, now you have 2 ways to proceed. When you have branch, you have 2 ways to proceed. And pipelining cannot do its job when there are 2 ways to proceed. Now, okay, I take it back. It can by doing both branches at the same time. And when the decision comes in, then it will abort whatever branch that is not reality. Okay? So the bottom line is loops are not, if you want something to execute fast, loops is not one of those things that can make things go really fast. So if you know that you need to do something like 12 times, a fixed number of times, instead of doing a loop to do it 12 times and increment a pointer, a counter, and then count it 12 times, if you just do it 12 times and expand it inline, it's a lot faster. Okay? And when you turn on certain optimizations of the GCC or G++ compiler, it will do it automatically for you. It will figure out, in what places, like when you have really tight loops, there's not a whole lot to do, but you're doing it like a fixed number of times. GCC can be smart enough to say, hey, I can inline expand that. Instead of an actual loop, I'm just going to do it like repeat the code like 12 times, 30 times, okay? You pay a small price in terms of code size, but you gain a lot in terms of performance. So there are optimization techniques in a compiler to go along with whatever architecture it's supposed to run on in order to make the end result code to execute as efficiently as possible. It's fun stuff, okay? If you want to become a compiler expert, it's actually really, really fun stuff. Especially with these new processors that we have, where it has multiple cores, but within a single core it has multiple ALUs. So the scheduling of how you make use of the most number of ALUs per core is also an issue, because now it has to do with how you sequence operations. There are alternative sequences. Like with a lot of things, you can change the order and not change the result. By changing the order, you can now utilize the ALUs more effectively in certain sequences, and in other sequences, it's not as effective. So they are all they're all fun stuff. Okay, and my roommate. Okay, I know we are out of time. My roommate from UC Davis. He's from EE. He's from electrical engineering, but his work was all compiler based. And he was hired. He got a pretty good job, after graduation. Just because there was a lot of need for people who can optimize compilers, and there are also people who tweak benchmarks. Okay, how do you decide which processor to buy? You look at benchmarks, right? And benchmarks can be tweaked. Okay, so if you're a processor manufacturer, there are things that you can do to optimize your processor to make the benchmarks look really good.
It's like teaching for the test.
Yep. But how about the general applications that are not benchmark programs? They may suck, but they will make the benchmark look really good. So there are people who do that too. I mean, those are well-paying positions, because they require a lot of in-depth knowledge, not only of the processor itself, but also compiler technology and the entire stack. You're talking about the entire stack, all the way from C code to the compiler, assembly code, processor architecture, processor sub-architecture, the microcode and all the ALUs in the inside, pipelining mechanisms, caching mechanisms. So you're looking at someone who has knowledge of the entire vertical stack. And those people are very few. Most people focus horizontally. Okay, you take the entire stack. Some people are very good with this segment of the stack. Some people are very good with that segment of the stack. But when you look down the entire stack, there are very few people who can look through the entire stack and figure out something to make it, to make the entire stack to achieve a particular outcome that needs stack height-wise coordination. So that's interesting stuff, just for you guys to consider. All right, we are getting out of the classroom, and if you are working on the homework assignment, let's go to the lab, and if you have questions, we'll go ahead and answer those questions.